Hi guys, in the last lecture we have solved some problem based on single phase half wave rectifier for both uncontrolled and controlled type. Okay, now in this lecture we will start single phase full wave controlled rectifier. So let us proceed to the first slide. So this is full wave controlled bridge rectifier having 4 thyristor T1, this is T3, this is T2 and this is T4. Okay, so T1, T2, T3, T4, 4 thyristor are connected in bridge form, and here the load is connected and supply is given Vs is equal to Vm sin omega t. So here I am assuming one thing, that is here load current is constant. I am assuming that I naught is constant. This is the I naught. Constant means here highly inductive load is taken. So highly inductive load is either RLE type or RL type of load I am taking, and I am assuming that load current is constant. Then I will do the operation. So this is the input supply voltage, this is Vm sin omega t Vs, and this is pi, this is 2 pi. Okay, also we can write like this: Vs is equal to Vm sin omega t, that is nothing but voltage across this AB. So VAB is equal to Vm sin omega t. Is it fine? And or I can say that VBA is equal to minus Vm sin omega t. So here input supply is given, that is Vm sin omega t, and I am triggering the thyristor T1 and T2. Thyristor T1 and T2 is this one and this one. I am triggering the thyristor T1 and T2 at an angle of alpha. This is at an angle of alpha. Then what will happen? See, from alpha to pi plus alpha. Okay, at omega t is equal to alpha, I am triggering thyristor T1 and T2, means this T1 and T2 will starts conducting from alpha. So equivalent circuit will look like this. Here you can see that T1 and T2 are triggered at an angle of alpha. So T1, T2 will be shorted, and in this case output voltage V0 you will get, that is equal to supply voltage. Output voltage will follow the supply voltage, that is equal to Vm sin omega t. And this is point A, this is point A, and this is point B. So I can also say V0 is nothing but VAB. If you will apply KVL, then VBA plus V0 is equal to 0. So VBA is equal to minus V0. So VAB is equal to V0 you will get from alpha to pi plus alpha. Now see here, most of the student got confused that after pi, this is pi. I am saying that from alpha to pi plus alpha, output voltage will follow the supply voltage. But here you can see that after pi, supply voltage is getting reversed. Means supply voltage is getting negative. This supply voltage is negative. That means this T1 and T2 must go into the reverse bias and it won't conduct, means it can be replaced by open circuit after pi. So most of the student got confused with this statement, right? See here I am assuming that load current is constant and you are not triggering T3 and T4 after pi. So what do you mean by this? This means to turn off this T1 and T2, I naught must be less than or equal to holding current of this T1 and T2 thyristor. Then only it will get turned off. But here I am assuming that I naught is constant, means the load is either RLE or RL type of load, which is highly inductive load. So even after reversing the supply voltage, this T1 and T2 has to conduct after pi, because load current is constant. Load current is not becoming less than equal to holding current, so it will not go into the off state after pi. So it will continue to conduct from pi to pi plus alpha also. The moment at t is equal to, at omega t is equal to pi plus alpha, you are triggering T3 and T4. So the moment when you will trigger the T3 and T4, then this T1 and T2 will go into the reverse mode and it will stop conducting. Before that it will continue to conduct, because this load current has to flow from any path, and here I am getting only one path, that is T1 and T2 before pi plus alpha, because you are not triggered T3 and T4. Is it fine? That's why after pi also this T1 and T2 is conducting even after reversing the supply voltage. Got it? Now if I will ask you, when this T1 and T2 are conducting, then what is the voltage drop across T3 and T4? Since T3 and T4 are not triggered from alpha to pi plus alpha, this means it will behave like an open circuit. So where is T3? T3 will lie somehow here. This is something like this, and it is connected to B, and the polarity of voltage drop across T3 will be from plus to minus like this. Okay, this is VT3. Now where is T4? T4 is connected to A. So T4 is something like this, and it is also open circuited from alpha to pi plus alpha, and it is connected like this, and the voltage polarity across T4 will be somehow like this, VT4. Okay, now apply KVL across this VT4 A point and V0 this. Apply KVL across this point. In this loop apply KVL. You will get plus VT4 plus V0 is equal to 0. So VT4 will come out to be minus of V0 from alpha to pi plus alpha. Okay, similarly if you will apply KVL in this loop, then you will get plus VT3 plus V0 is equal to 0. So here also VT3 will come out to be minus V0 from alpha to pi plus alpha. So I can say that if T1 and T2 are conducting, then at that time the voltage drop across T3 and T4 is nothing but minus of V0. Got it? So from alpha to pi plus alpha, see, from alpha, this is alpha and this is pi plus alpha. Output voltage will follow the input voltage, that is something like this. Output voltage will follow the input voltage from alpha to pi plus alpha. Okay, so in this reason voltage drop across T1 and T2 will be 0 because it is replaced by short circuit. So voltage drop across T1 and T2 will be 0 from alpha to pi plus alpha. This is voltage drop across T1 and this is voltage drop across T2. But the voltage drop across T3 and T4 I will get that is equal to minus of V0. See, the V0 is somehow like this from alpha to pi plus alpha. So minus V0 will be just opposite to this V0. So minus V0 will be somehow like this. It will follow like this from alpha to pi plus alpha. This is pi plus alpha. So voltage drop across T3 and T4 will be look like this. So if I will ask you what is the circuit turn of time, then circuit turn of time is defined as the time for which thyristor is in reverse bias. So here the thyristor is reverse bias from alpha to pi only. This is circuit turn of time. So circuit turn of time will be pi minus alpha upon omega. Okay, now what is happening after pi plus alpha means at pi plus alpha I am triggering T3 and T4. T3 T4 is triggered. So the moment when T3 T4 is triggered, then the circuit will look like this. See here, the circuit will be like this. When you trigger the T3 and T4 at pi plus alpha, then T3 T4 can be replaced by short circuited, and it is replaced by the short circuit and the circuit will look like this. So in this case also you can see that output voltage will come out to be, apply KVL here. Let us say I am applying KVL from here. So plus V0 plus VAB is equal to 0, plus V0 plus VAB is equal to 0. So V0 will come out to be minus VAB, or I can say that VBA. So from pi plus alpha to 2 pi plus alpha, output voltage I will get that is equal to VBA. So VBA will somehow look like this. So from pi plus alpha to 2 pi plus alpha, output voltage I will get that is equal to VBA. And in this case also, if you will found the voltage across thyristor T1, this is voltage across thyristor T1, that is VT1, and this is connected like this, and this is voltage drop across thyristor T2, VT2 from polarity like this, then you will get VT1 T2 is nothing but minus V0, same as the previous case. Got it? So after pi plus alpha, T3 T4 will start conducting and T1 and T2 will go into the reverse bias. You can see that this T3 is connected with B and VBA is nothing but positive terminal. B is positive terminal after pi plus alpha. So this will be in plus and this will be in minus. So supply voltage is negative when T3 T4 are conducting. That means the voltage drop across T1 and T2 will be negative, and in this case T1 T2 stops conducting from pi plus alpha to 2 pi plus alpha. So in nutshell I can say that from alpha to pi plus alpha T1 T2 will conduct, and from pi plus alpha to 2 pi plus alpha T3 T4 will conduct. So if I will talk about the steady state, then we can easily say that from 0 to alpha T3 T4 is conducting, because here the load current is constant. So at any time any two thyristor must conduct. So from T1, when T1 T2 is conducting, then T3 T4 will be off, and when T3 with T4 will conduct, then T1 T2 will be off. Got it? In this way the cycle repeats. Now if I will talk about the source current, how the source current will look like, see here. See, from alpha to pi plus alpha, from alpha to pi plus alpha, which thyristor is conducting? T1 T2 are conducting. Okay, so if I will have to draw the equivalent circuit, then equivalent circuit will look like somehow this. From alpha to pi plus alpha, T1 T2 are conducting, means equivalent circuit will be somehow look like this. This is the source current. Source current is nothing but this is the source current. So source current from alpha to pi plus alpha, you can see that source current is nothing but I naught only. So from alpha to pi plus alpha, Is is equal to I naught, means source current will follow the load current. Okay, now what will happen from pi plus alpha to 2 pi plus alpha? See, from pi plus alpha to 2 pi plus alpha, T3 T4 are conducting and T1 and T2 are off. So if I will have to draw the equivalent circuit, then equivalent circuit will look like this. Okay, and here the source current is from left to right. By default source current I am taking from left to right. I naught is flowing like this. Okay, see this is the current direction of I naught, and you can see that source current is opposite to the load current. So in this case Is will be minus of I naught. Okay, so from pi plus alpha to 2 pi plus alpha, this is 2 pi plus alpha, source current I am getting, that is minus I naught, that is look like this. Is it fine? So in this way we can make the output voltage waveform, voltage drop across thyristor and the source current. Got it? Now find some important parameter. Take a note. First find the what is the output average output voltage, V naught average. V naught average is like this. So waveform is like this. So average output voltage, see the time period of output voltage, that is equal to 1 upon pi, and it is conducting from alpha to pi plus alpha, Vm sin omega t, d omega t. Find this, you will get 2 Vm upon pi into cos alpha, and this is the most important relation of output voltage. Most of the question are framed from this average output voltage, that is 2 bm upon pi into cos alpha in full wave controlled bridge rectifier when I naught is constant. When I naught will be discontinuous, then this formula is not valid. Okay, so for continuous I naught only this formula is valid. V naught average is equal to 2 bm upon pi into cos alpha. Now second point is, you have to find the circuit turn of time. We have already find the circuit turn of time. See, the thyristor is reverse bias for the period of pi minus alpha, that is equal to pi minus alpha upon omega. Now see the third point. The third point is, we have to find the thyristor current. See, each thyristor is conducting from alpha to pi plus alpha, T1 T2 is conducting, and from pi plus alpha to 2 pi plus alpha, T3 T4 is conducting. Means I can say that each thyristor is conducting for the period of pi. So if I'll have to find the conduction period of thyristor T1, then I can easily draw the waveform like this. From alpha to pi plus alpha, T1 is conducting, and this is equal to the load current I naught. Maximum current is load current only. So this is the conduction angle of thyristor T1. Similarly, the conduction angle of thyristor will be look like this only in one period. Now if I will have to find the conduction angle, this is the conduction angle of thyristor T1 and T2. Now if I will have to find the conduction angle of thyristor T3 and T4, then T3 or T4 are conducting from pi plus alpha to 2 pi plus alpha. Is it fine? And the current will be somehow like this. This is the maximum current. The current is equal to the load current only. Okay, now find the average thyristor current and RMS thyristor current. So IT average will come out to be, see here, IT average is nothing but conduction angle is like this. So I have already explained you how to find the average value and RMS value in lecture number 8, that is equal to rectifier and its classification. See the last 5 minutes of lecture number 8, you will understand how to find the average and RMS value of a square or rectangular pulse. So average IT average will come out to be maximum current, that is I naught, into for how many period it is conducting. It is conducting from alpha to pi plus alpha, that is equal to pi. Conduction angle is pi, and what is the time period? Time period is 2 pi. So I naught average will come out to be I naught upon 2. Similarly, IT RMS, we can find the thyristor RMS current is nothing but maximum current under root of conduction angle. For how many angle it is conducting? It is conducting up 4 pi and time period is 2 pi. So I naught upon root 2. Okay, this is third point. Now take one note, that is we are getting V naught is equal to 2 Vm upon pi into cos alpha. Means output voltage are depending upon the triggering angle, that is the alpha. Okay, so if alpha will be less than 90, means cos 90, cos less than 90 will always be positive. So V naught I will get greater than 0 and I naught is also greater than 0. So in this case P naught will be greater than 0. So we can say that power is transferred from source to load. Okay, now what will happen if alpha is greater than 90? For alpha greater than 90, this V naught will be less than 0 and I naught is always greater than 0, that is constant. We can see here that, so P naught will come out to be less than 0. So output power will be negative. What do you mean by this? This means power is transferred from load to source. We have done this case in earlier rectifier circuit also. So we can say that for alpha greater than 90, this converter will behave like an inverter. What is inverter? Inverter is which convert DC power into AC power. So for alpha greater than 90, DC power, that is the load power, is transferring to the source. So we can say that for alpha greater than 90, this converter will work as an inverter, and for alpha less than 90, this converter will act like a rectifier. Okay, this is very very important, so keep in mind. So I can conclude that here the bidirectional power flow can be possible. What do you mean by this? Bidirectional means the power is flowing in both the direction, from source to load as well as from load to source. Now let us do the harmonic analysis of source current. We should know how much harmonic content are present in the source current. Because of rectifier circuit, the source current is not sinusoidal. It is a rectangular pulse repeating from plus I naught to minus I naught. Source current I am getting like this. This we have discussed earlier. We have derived in the previous lecture, that is equal to summation of n is equal to 135 to infinite 4 Vs upon n pi into sine n omega naught t minus n alpha. It is shifted by an angle of alpha. We have derived this Fourier series in lecture number 7. Okay, so go through that lecture, you will understand how I am getting this. So if I'll have to find the Fourier series of this source current, then this source current is nothing but it is shifted by at an angle of alpha. So source current, the Fourier series of source current will be summation of, only odd harmonics will present, 135 up to infinite 4 I naught. This is the maximum current, that is I naught. Okay, so 4 I naught upon n pi sine n omega naught t minus n alpha. This is the Fourier series of this source current waveform. Okay, now find the IS1 RMS, means fundamental RMS component of source current. IS1 RMS is nothing but, put n is equal to 1 here. This is the maximum value, and maximum value divided by root 2 will give the RMS value. So we can say that IS1 RMS is equal to 4 I naught upon n pi, n is equal to 1 divided by root 2. So this will come out to be 2 root 2 I naught upon pi. This is the IS1 RMS. Now source current RMS will be what? This is the source current waveform. So to find the RMS value, what I told you that square the waveform, then find the average of that waveform, and third, take under root. That will give you the RMS value of that waveform. So if I will square this waveform, then it will be something like this. The source current will be something like this, and the maximum value will be I naught square. Now average of this waveform is nothing but I naught square only. So IS RMS will come out to be under root of this I naught square, that is equal to I naught. So IS RMS is equal to I naught. Now find the distortion factor G. G is nothing but IS1 upon IS. So you will get 2 root 2 upon pi. This is equal to 0.9. Now find the THD. THD is nothing but under root of 1 upon G square minus 1. So THD will come out to be 48.34. Now find the input power factor. So to find the input power factor, I told you the procedure, that is equal to always put P in is equal to P out. You can find like that also. And here input power factor I have derived in the previous lecture, that is the lecture number 10b. So if you have gone through my lecture number 10b, then I derived that that input power factor is nothing but G into fundamental displacement factor, where fundamental displacement factor is nothing but cos of angle between the fundamental source voltage and fundamental source current. So here source voltage, fundamental source voltage is nothing but Vm sin omega t only, because there is no any harmonic present in source voltage. Source voltage is always sinusoidal. So fundamental source voltage Vm sin omega t, while fundamental source current, if I'll have to find the fundamental source current, then the fundamental source current Is1 will come out to be 4 I naught upon pi sin omega naught t, put n is equal to 1, minus alpha. So you can see that the angle displacement between fundamental source voltage and fundamental source current is nothing but alpha. Source current is displaced by an angle of alpha, so fundamental displacement factor will come out to be cos of alpha. So input power factor is equal to G cos alpha, that is equal to 2 root 2 upon pi into cos alpha. Okay, you can follow this approach, that is input power factor is equal to G into fundamental displacement factor, or you can also find the input power factor by putting P in is equal to P out also. So whenever you know the Fourier series of any kind of waveform, then to find the input power factor use this formula, and if you don't know the Fourier series of any kind of waveform, then for finding the input power factor always put P in is equal to P out. So let us verify input power factor by putting P in is equal to P out. See, for finding the input power factor, what we are doing, we are putting P in is equal to P out, where P in is equal to Vs Is cos phi, that is equal to P out. Here I am taking voltage stiff type of load or current stiff type of load. Here see, I am taking load current is continuous, and I am taking RLE type, and this is possible only when the load is RLE or RL type. So this is nothing but current stiff type of load. So in current stiff type of load, output power is nothing but V naught average into I naught average. Okay, right, Vs Is cos phi, V naught average is nothing but 2 Vm upon pi into cos alpha, and I naught average is I naught. Okay, and I have already derived source current. Source RMS value of source current is equal to load current in this case. Cancel this, Is is equal to I naught. You will get cos phi is equal to 2 root 2 upon pi into cos alpha. You are getting same as this. So either you can follow input power factor is equal to G into fundamental displacement factor, or you can go through by putting P in is equal to P out. You will get the same. Both are the right approach. You can go by any approach. So let us summarize what formula we got in this full wave controlled bridge rectifier taking load current as a continuous. So you have to remember these all things that we have discussed in this lecture, that is V naught average is equal to 2 Vm upon pi into cos alpha. I naught is continuous, means their RMS and average value are equal. Circuit turn off time, that is equal to pi minus alpha upon omega. Also conduction angle of thyristor I was getting from alpha to pi plus alpha, that is equal to pi. So if I will have to find the IT average, then IT average will be I naught into conduction angle pi upon 2 pi, that is equal to I naught by 2, and IT RMS, thyristor RMS current, is nothing but I naught under root conduction angle it is conducting from pi to 2 pi, that is equal to I naught by root 2. So this formula you have to keep in mind. Now you should also remember the Fourier series of this waveform, source current waveform. Source current will look like somehow this from alpha. So it is shifted by an angle of alpha, and we have derived the Fourier series of this waveform in lecture number 7. Okay, so go through that lecture, you will understand how this Fourier series is coming. Now fundamental displacement factor is the angle between, the cosine of angle between fundamental RMS current and fundamental RMS voltage. So angle between fundamental RMS current and fundamental RMS voltage is equal to alpha. So fundamental displacement factor will come out to be cos alpha. Also Is1 RMS, to find the fundamental source RMS current, only you have to put the n is equal to 1 and find the Im. Im you will get 4 I naught upon pi, and Im by root 2 will give you the RMS value, that is equal to 2 root 2 upon pi into I naught. Now Is RMS we have found, that is equal to I naught only. So Is1 upon Is will give you the distortion factor, that is equal to 2 root 2 upon pi, and TSD will come out to be 48.43%. Now the last one, that is the input power factor is equal to G into fundamental displacement factor. If Fourier series you know, then you can find like this, that it will come out to be 2 root 2 upon pi into cos alpha. Or if you don't know the Fourier series of any kind of waveform and you want to find the input power factor, then put P in is equal to P out and you can find the input power factor by putting P in is equal to P out. That's all about this lecture. In the next lecture we will see single phase, full wave, semi-controlled converter. There are three converter, that is symmetrical, asymmetrical and full converter with freewheeling diode. So we will discuss one by one. If you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving you can join our Facebook group. Thanks for watching this video.